Good morning students. Welcome to fifth video on system of particles and rotational motion. In the previous video we came to know that the concept of velocity of center of mass of system of particles and acceleration of center of mass of system of particles. So in this video we will learn linear momentum of center of mass of system of particles and vector product of two vectors. First let us consider linear momentum of center of mass of system of particles. Suppose if you take the system of particles having masses say m1, m2 etc. with the velocities v1, v2 etc. Then linear momentum of individual particles can be written as p1 is equal to m1 v1 vector, and similarly a second particle linear momentum can be written as m2 v2 vector and so on. So now if Pc is total linear momentum of all the system of particles, then we write Pc is equal to P1 plus P2 plus so on plus Pn, where Pc is linear momentum of the center of mass of system of particles, P1, P2 etc. are the individual linear momentum of individual particles. So we call this as equation 1. We know that since Pc is equal to total mass, linear momentum of center of mass can be written as total mass of the system of particles into velocity of center of mass, and P1 is equal to m1 into v1, then this equation 1 can be rewritten as m into Vc is equal to m1 v1 vector plus m2 v2 vector plus so on mn into vn vector. Mn into Vn vector. So you call this as equation from equation 1 and equation 2. The linear momentum of center of mass of the system of particles can be written as Pc is equal to m into Vc. So we call this as equation C. This is the expression for linear momentum of system of particles. Linear momentum of center of mass of system of particles, which can be written as Pc is equal to m into Vc. Suppose if you differentiate this equation with respect to dt, differentiate equation 3 with respect to dt. So then we get dPc divided by dt, which is equal to m into dVc divided by dt. You know that dVc divided by dt is equal to AC. So that is since dVc divided by dt is equal to AC, called acceleration of center of mass, then dPc divided by dt, change in linear momentum of center of mass, written as m into AC, which is equal to F that is product of mass into acceleration is external force. Suppose if Fext is equal to 0, if external force is equal to 0, then dPc divided by dt, which is equal to 0, or linear momentum of center of mass of system of particles Pc is equal to constant. So thus we can define law of conservation of linear momentum for system of particles as when no external force acting on the system of particles, then center of mass of the linear momentum remains constant. constant. So this is law of conservation of linear momentum for system of particles. It says that when no external force acts on the system of particles, then linear momentum of center of mass remains constant, with all the particles moves with a constant velocity because no external force acts on the system of particles. So this is about linear momentum of center of mass. So now we shall move to vector product of two vectors. Vector product of two vectors. So vector product of two vectors is defined as the product of magnitude of two vectors into sine of angle between them. The product of magnitude of two vectors into sine of angle between them is called as vector product, or it is also called as cross product of two vectors. Suppose if you take the two vectors which are acting at a point, say O, with an angle theta, then the cross product of these two vectors, say A and B, is another vector C, which can be written as vector C is equal to A cross B. Thus, the cross product of two vectors is equal to another vector C, where C vector has a magnitude of product of magnitude of these two vectors into sine of angle between them into n cap C, where n cap is a unit vector which is in the direction of C vector, where C vector is always perpendicular to both A and B vectors. So the direction of the cross product of vector product of two vectors can be taken like this. Suppose if this is A vector and this is B vector, then according to right hand rule, if you move from vector A to vector B like this and curling your four fingers which are in the direction from A to B, then the thumb which is pointing upward is the direction of the A cross B. Suppose if you move from A to B, then cross product of A cross B is upward. Then when you move from B to A, the direction of A cross B is downward. So therefore, cross product of two vectors is another vector whose direction is perpendicular to both the vectors, say vector A and vector B. Then the magnitude of C vector, that is cross product of two vectors, depends on the angle also, that is if theta is equal to 0, then the cross product of these two vectors is minimum, because sine 0 is 0, then we will get a null vector in that case. If theta is 0, then cross product of two vector is 0 vector. Then if theta is equal to 90 dB, and we will get the magnitude of this cross product of two vector is maximum, it is A cross B is equal to AB. So then we have some identity related with the vector products. So vector product is obeying distributive law. Vector products obeys distributive law, which means vector A cross vector B plus vector C. Then this can be written as vector A cross vector B plus vector A cross vector C. So thus vector product of two vector obeys distributive law, but vector product of two vector is non-commutative. That is, we can say that A cross B is not equal to B cross A. The direction of A cross B is not same as the direction of B cross A. Thus, vector product of two vector is non-commutative, but therefore it's good. distributive law. So that is cross product of two vectors is defined as the product of magnitude of two vectors into sine of angle between them, and therefore we say A cross B is equal to AB sin theta into n cap, and this AB sin theta into n cap can be treated as another vector. So the cross product of two vectors can yield the another vector, we say C. For example, if you take cross product of position vector into linear momentum, we say R cross P is equal to angular momentum vector, which is cross product of two vectors. It is equal to angular momentum vector. Similarly, if you take cross product of position vector into force, which we will get torque, which is represented by tau vector, and therefore torque and angular momentum are the examples for cross product of two vectors.